Yeah, I could just write S sub k plus k plus 1 equals S of k plus 1. The sum of the first, 100 terms plus 101 equals the sum of the first 101 terms. The sum of the first 5 terms plus 6 equals the sum of the first 6 terms. Does that make sense?
Yeah.
Okay, if we can algebraically prove that this is a true statement, that these two sides are equal, then we'll have proven that these two rungs of our ladder have this property, and then we can assume that this formula works out to infinity and start using it all we want. If we can't prove it, I know mathematical induction is a little weird. It's not really an assumption, but
I have a question.
We behave like one. Yes?
So the k plus 2, that's because of the...
That's because we put k plus 1 in for k up here.
That's what I thought.
Yeah. Okay, so this is, I keep using number examples. If this were the sum of the first 7 terms, this would be the sum of the first 7 terms plus 8. Which should be the same thing. And if this is the sum of the first 8 terms, then that should be equal to the sum of the first 7 terms plus 8. Does that make sense?
Yeah, I think.
Yes.
And that doesn't make any sense algebraically. That the first part, they don't equal each other.
Well, let's find out.
No,
Take a look at this. Okay, here's what I'm going to do. I'm going to make a common denominator, right?
Yeah, and that doesn't equal out to be the same thing.
It should, or else we're in trouble. Right?
Yeah.
You may be right, and this is maybe about to blow up in my face. Let's find out. No, hang on.
Doesn't work.
Okay, so this is going to be k squared plus k plus 2k plus 2, right?
Yeah.
All over 2. And over here, if I FOIL it, I'm going to get k squared plus outer 2k plus inner 1k plus last 2 all over 2.
This is so much fun.
What?
Where did you get the 2 from?
I made a common denominator between these two fractions.
Oh, okay.
So I had to multiply top and bottom by 2.
Okay.
Then I distributed and made one big fraction, and over here I just FOILed. Now since I've proven that the sum of my conjecture for the sum of the first k terms plus the k plus 1 terms is equal to my conjecture if I put in k plus 1, I can now use that rule and know it'll work up to infinity. So the two rules are, 1, verify the formula for n equals 1. 2, verify the formula for the k plus 1th term in terms of the kth term.
Do you mean this?
I used n over there, yeah.
But is it the sum of the k plus 1?
Yes, you're verifying the sum formula.
Just...
Yeah, with it. And this is used to prove people's guesses. Like, okay, little Carl Friedrich Gauss came up with his rule when he was 10, right? But in math, you don't believe anything or you prove it absolutely. Even if something works for the first 100,000 attempts, the first 100,000 numbers you plug in, doesn't mean it won't fail for the next one. Doesn't mean it really does work up to infinity. This is one of the more clever and, believe it or not, simpler proofs mathematicians came up with. This process of mathematical induction to prove all those little formulas that Carl was throwing at you and that we were giving actually always work.
What is your reason for saying it's simpler?
Doesn't take up 20 pages?
Yeah.
Yeah, this is one of the simpler proofs. This is one of the simpler examples of it. Here, I'll give you an historical example, and then I'll do another example of something that isn't necessarily much more practical, Jesse, but it's a little less abstract.
You do
okay?
it like real numbers, not with K's.
Yeah.
No, actually you can't, because proving it for any two real numbers only proves it works for those two numbers. Proving it in terms of k means it works for any two numbers we can imagine.
So if they give you one, whatever you just said, prove that.
Yeah.
Then what do you plug in for k?
No, nothing. You plug in k in the first one, k plus 1 into the second one.
So you don't use any numbers, you're just using variables?
Correct.
So then where does that
Wait, so
whole
then there's no
number
point. Wait, so if you give us that on a test, we just write k squared plus k plus 2k plus...
No, I won't give you this one on a test. Or if I do, you'll be lucky. There's a million other formulas, and there are a million other ways you can use this. This is just for one sum formula. And this isn't even the only sum formula. Remember, this is different from what Carl came up with. You know, all those different arithmetic and geometric sequences we did with the sigma signs? You can come up with a formula like this for any of them, and then you got to prove it works out to infinity.
Because of that
So you can prove all of them, though.
Yeah,
And
well,
also-
all of them can be proven. I don't know that I could.
K plus 1 just represents n plus 1, right?
Yeah,
So the K, you just substitute for the n and it works.
yeah. That's just a bit of pickiness on your book part because it likes to use n for the general idea and k for some specific example, but we're not going to say which it is.
Put it over to is for that formula, right?
Yes, that's the only reason because this is the formula you're given.
Alright.
You're not going to be asked to come up with any on your own. Okay, you're going to be given something to prove.
Wait, we
follow
have
me.
to prove?
Pardon?
We have to prove our...
This was a proof, yeah. Okay, now, I'll give you a specific example. I cannot do this proof. In fact, there's about 8 people on the planet who can do this proof, but I can describe it to you.
Yeah, seriously.
Okay, just an example of the sort of thing this is used to prove.
Okay, can you, like, fix this?
Okay, now, there's a guy named Pierre Lafermat. He was around at the same time of René Descartes and Viette and a couple other mathematicians. He was a math genius. In some ways, I think he may have been the most brilliant of them all because math for him was a hobby. He was a lawyer. He did math on nights and weekends. He kept up with the biggest math dogs of Europe in the 1600s. Here is one of his ideas. Tell me if this looks... Okay, I'll do it this way. Tell me if this looks familiar.
Yeah. Pythagorean theorem.
Looks like the Pythagorean theorem. The Pythagorean theorem, what does n equal?
2.
2. Okay. You know how the Pythagorean theorem has those triples that work? 3, 4, 5, 5, 12, 13, 9, 40, 41, plus all of their multiples? Here was Fermat's idea. In the early 1600s sometimes, in the margin of one of his math notebooks, he wrote that he had absolutely proven that these triples, these whole number triples, never, ever, ever occur if n is greater than 2. So if you have a cubed plus b cubed equals c cubed, you can have cube root answers. You can have ugly irrational nests. You can have decimals that work that go on forever. But you'll never have like another triple like this, nice whole numbers. If you have a to the 4th plus b to the 4th equals c to the 4th, you'll never get nice, neat whole numbers, all 3 of them. That'll work. Yes?
What if it's like n equals 1 or n equals 0? You won't.
He had to
have
discount
that
those
either.
cases, yes. You know what? I should have. That's why I said greater than 2.
Yeah, but less than 2 also.
Less than 2? Well, sure. If a equals 1, I can just say 2 plus 3 equals 5.
Yeah. No, but like.
But
His
But if it equals 0.
Pardon?
Let's say n equals 0.
Then you have 1 plus 1 equals 1.
But it's 2.
Right, but 1 works. And negative exponents are different. Now, and 1 works fine, because then a, b, and c can be any number itself. Anything raised to the first power is itself.
Yeah, but 1 plus 1 equals 2, not 1.
Sweetie, if this is raised to the first power, if n equals 1, then this can be any number at all. This can be 3 plus 5 equals 8.
I'm saying if it's raised to 0.
Yeah, then it doesn't work also.
I know.
You're right.
That's what
But
I'm
that
saying.
wasn't his proof. He only cared about n greater than 2.
Fine.
Okay, and he's using n because it's whole numbers. 3, 4, 5, 6. Okay?
Whatever, I'm just saying it doesn't work if it's
0?
less than 2.
But it does actually work for n equal 1.
Fine. Fine.
Okay?
Fine.
Alright, so glad we got this straightened out. Now, here's the deal with this. He wrote in the margin of his book in the early 1600s, I have discovered